Okay, continuing our discussion, we're going to start to look at Le Chatelier's principle and what that has to do with equilibrium and changing the equilibrium state of a reaction. So let's imagine that this seesaw represents our reaction at equilibrium. And so there's not the same number of reactants and products present, but that's because sometimes a reactant could decompose and form two products. I'm just using that as a model to present that. But these are balanced in a way that we have the equilibrium state where they are the forward and reverse rate are considered the same. So in this analogy, the force being applied by the reactants in red are balanced out by the force applied by the products in blue. So let's imagine that I added a couple of reactants, red circles, to our equilibrium state. And that would throw it off balance and cause it to no longer be in equilibrium. And so this is representing that in B. But the question is, what could we do to be able to restore this equilibrium? So in question 3 down below, I say, okay, so how can we restore the equilibrium? So the answer would most likely be that some of your reactant has to convert into product, or red circles must convert into blue circles. And so that means I would take one of those red ones and move it to the other side, which in this case represents the chemical reaction being pushed in the direction of product. Okay? And so then here we have a restored equilibrium with product formed and balanced out with our reactant. So this brings us to Le Chatelier's principle. When you have a reaction at equilibrium, you can shift the reaction in one direction or another, which basically means make the concentration of products or reactants higher based on whatever condition you're altering. So one example is if we were to change the temperature. And since we have way more of reactant, which is represented by red here, than product, when you increase the temperature, the kinetic energy in this box is going to increase, and so will the kinetic energy in this box. But there's way more stuff over here, and so the collisions will occur much more frequently, which will cause the reaction to shift this direction. And that's kind of an oversimplification, but that's the prediction that we can make based on the amount of stuff that's in each box. So you increase the temperature, and now you can see that the amount of red and blue circles are pretty equal. And a new equilibrium is established at this new temperature. Okay? So then let's look at the second example. If we increase the concentration, we can predict what will happen when we to our equilibrium if we were to add more of product C. So basically just increasing the concentration of product C. So if we add more C, that means we're adding this one. That's when the reaction is in equilibrium, we had A plus B on one side, and we have C plus D on the other side. And then once we add more C, for example, we could have still A plus B on this side, but now we have two C's plus D, and our reaction is thrown off balance. So in order to restore balance, something from this side needs to shift back that direction. And so the restored balance will be with more of reactant. So the amount of reactant has increased and the amount of product decreased a little bit in order to restore that balance. Okay? So basically, whatever side of your reaction you're adding stuff to, the reaction will shift the other direction to make up for that and be able to re-equilibrate. So here are some of the different things we could change in order to shift the reaction, like what we're talking about with Le Chatelier's principle. You could increase the concentration of a substance, like we just did with C. You could decrease the concentration, so take away something. If you were to take away something from one side, that side would become lighter, and the reactant or whichever other side would need to form product to be able to go back towards that substance and reestablish that equilibrium. You could increase the pressure or decrease it in a gas system, and you could change the temperature of the reaction. If you add a catalyst, that should not have any effect on the equilibrium constant, but it will affect how quickly your reaction can get to equilibrium. And these are all the changes that we could possibly make to in our examples right now. We're going to discuss this a little bit more thoroughly in class, but just remember, whichever side you're adding to, it's going to shift away from that direction, and whichever side you're taking away from, it will go towards the side that you shifted, that you reduced. Hopefully that made some sense. But it should make more sense in class for sure. All right, that's it.